All right, go to the notes for section 9.1, which is the basic combinatorics. So this is how you count things essentially, or combine things. So the importance of counting. So how many different ways can three distinguishable objects be arranged in order? So we'll just call them A, B, and C. So we'll start with A, then we can choose B, then we can choose C, or we can do A, then C, then B. Or we can start with B, then go A and C, B, C, then A, and lastly, you can start with C, A, then B, C, B, then A. So 1, 2, 3, 4, 5, 6. So there are 6 ways that are distinguishable, meaning they're different from each other. So this is what's referred to as the counting principle. So if your first object, now you can also combine this together essentially. With procedure, P has a sequence of stages, S1 is to Sn, all the way up to however many stages you want to do. S1 can occur R1 ways, S2 can occur N2 ways, Sn can occur Rn ways. The total number of ways the procedure can be occurred is just the product of all the ways that the individual things can be chosen. So, let's look at example 2 here. Tennessee license plate consists of 3 letters of the alphabet, followed by 3 numerical digits, 0 through 9. Find the number of different license plates that can be formed if there is no restriction on the letters or digits. So essentially, we've got 3 places to fill, 3 places to fill. So 3 letters of the alphabet. So I can put any letter here I want. So I have 26 choices. I have another 26 choices and another 26 choices. And then for the digits, there are 10 different digits, 0 through 9. So the total number of ways that I can make this selection is 26 times 26 times 26. Oops. Times 10 times 10 times 10. So there are 1, 7, 5, 7, 6, 1, 2, 3. So there'd be 17 million different license plates. Now, if no digit or letter or digit can be repeated, so I have 26 options for the first letter, but then I only have 25 options for the second because I can't use whatever was there. And here I only have 24 choices because I can't use either of those 2. Digits, I can use any of the 10 digits, but now the second one I can only use 9 because I can't repeat that one. Here I can only use 8 because I can't repeat those 2. So 26 times 25 times 24 times 10 times 9 times 8 would be 1, 1, 2, 3, 2, 1, 2, 3 zeros. So there's 11 million license plates if you do not allow any repeats. Okay, so we also have what's referred to as a permutation. So this symbol here is the factorial symbol. It means multiply by every essentially whole number down. So n factorial is the same thing as n times n minus 1 times n minus 2, all the way down till you hit 1. So for example, number-wise, if you do 4 factorial, that's, 4 times 3 times 2 times 1. Every whole number down to 1. Also, 0 factorial is defined to be 1, even though it doesn't mathematically follow that pattern. So permutation is an arrangement in which order does matter. So there are n factorial distinguishable permutations of an n set containing n distinguishable objects, meaning that they're all different from each other. If an n set contains n1 objects of the first kind, n2 of the second kind, and so on and so forth, the number of distinguishable permutations looks like this. So this stuff on the bottom takes care of any repeats. So what that would look like down here, count the number of distinct 9-letter words. So just they're using arrangements of letters to be words here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 letters here. None of them repeat. So it's just 9 factorial. So let me find the... Most calculators have a factorial button. So there are 362, 880 different arrangements of those letters. So for butterfly, there are 9 letters total. However, we have 2 T's, so we'd have to divide by 2 factorial. Means that one letter repeats twice. So this would be 181,440 different arrangements of those letters. Now, bumblebee has 9 letters. However, there are 1, 2, 3 B's, so there's something that repeats 3 times. And then there's 3 E's as well, so 3 E's that goes on the bottom. So 9 factorial. So you have a different factorial on the bottom for everything that repeats, and the number is the number of times that thing does repeat. So in Bumblebee, there's only slightly more than 10,000 different ways you can arrange those letters. Okay, so here's the formula for permutations. If you're selecting a group of R of them, so you have n total objects, you're selecting R. So it looks like this, n factorial divided by the difference factorial. So you evaluate the expressions. So here's my n value. So for this problem, n is 6 and R is 4. So it's 6 factorial over 4 factorial. Now you could work this out, but 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, and 4 factorial is 4 times 3 times 2 times 1, so those all cancel. So it's just 6 times 5, or 30. So, oops, nope, I did that wrong. It's not 4 factorial on the bottom, it's the difference on the bottom. It's 6 factorial over 2 factorial, which means that only the 2 and the 1 cancel. So you have 6 times 5 times 4 times 3 times 2 times 1, all over 2 times 1. So those cancel. So 6 times 5 is 30, times 4 is 120, times 3. So there's 360 different ways that I could elect a group of 4 out of a group of 6 if order matters. So here, 11 groups. So this would be 11 factorial over 8 factorial, the difference. Now you can kind of shortcut this. I have 3 spaces to fill, and I have 11 choices total. So the other way to think about it, if you go back to our license plate problem, there's 11 choices for the first, and then there's 10, and then there's 9. So it would look like this. So there are 990 different ways, or if you work it out mathematically, you'll get the same thing. Mostly because if you do 11 factorial, that's 11 times 10 times 9 times, and then 8 factorial divided by 8 factorial. Those cancel. There you go. So n, 3. Now this one is much easier because if you try to do the formula, you get this. But the thing is, n factorial is n times n minus 1 times n minus 2 times n minus 3 factorial and everything after it. And on the bottom, you have n minus 3 factorial. Those cancel. So this is just whatever this works out to be. Okay, example 5, 16 actors answer a casting call to try out for roles as dwarfs in a production of Snow White and Seven Dwarfs. How many different ways can the director cast them? So I have 16, and I need to choose 7. So it'll look like this. So this would be 16 factorial over 9 factorial, which would be 12 times 11 times 10 times 9 factorial, and on the bottom, so those cancel. So it's just 16 through 10 multiplied together. 16, but I'll just do it the short way. So there are a lot of different ways that you can cast those. So it is 57,657,600 different ways those 16 actors could be cast. Okay. So combinations are similar to permutations, but order doesn't matter. So I just need to randomly select a group, and it doesn't matter. There's no assignment for who's picked first, second, or third. That's a combination. Permutation means there's specific roles assigned with each selection. So choosing a president, vice president, secretary for class officers, that would be a permutation. If you just need 3 class officers, that would be a combination because they're all 3 the same. So the only difference is you multiply by the difference and the number you're selecting total. Okay, because that takes care of the repeats essentially, because choosing person A, B, C is the same as choosing C, B, A, because order doesn't matter once you select them. You still have the group of letters A, B, and C. So in each of the following scenarios, till a permutation or a combination are being described: president, vice president, secretary. So this has 3 specific roles. So this is a permutation. Cook chooses 5 potatoes from a bag of 12. This is a combination. It doesn't matter which potato is picked first. Teacher making a seating chart. Well, since order would matter, if I pick your names in a different order, you have a different seating chart. Oops, permutation. Okay, Miss America pageant, 51 contestants must be narrowed down to 10 finalists who will compete in national television. How many possible ways? So this doesn't matter which order they are chosen. I just need to pick 10. So this would be 51 factorial over the number I'm picking times the difference. Now this is just going to be the calculator. So 5 factorial divided by 10 factorial divided by 4 factorial. Oops, sorry, 51 factorial. I got a very small number there. So this is a ridiculous number. Because I keep forgetting typing it in my calculator wrong. Either did 5 or I did 40, or 4 instead of 41. There we go. So it is 1,2,1,777,1,1,870. So there are 12 billion different ways which they can be selected. So a group of 10 out of 51. Okie dokie. So lottery numbers here. The Georgia Jumbo Bucks lottery requires players pick 6 integers between 1 and 47 inclusive. The order in which the player selects them does not matter. Indeed, the lottery tickets are printed with the numbers in ascending order. How many distinct lottery choices are there? So let's see here. There are 47 numbers total. I need to choose 6 of them. So 47 factorial, I'm choosing 6, and the difference is 41. And this all just goes in my calculator. 47 factorial divided by 6 factorial divided by 41 factorial. So 107,375,73. So there are 10 million different possible tickets. All right, subsets of an N set. So Armando's pizza offers patrons any combination of the 10 different toppings, pepperoni, mushroom, sausage, blah, 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 blah. How many different orderings if we choose any 3 toppings? So I have 10 choices for the first, 9, and then 8. No, but I guess order doesn't matter, so I can't do that. I need a combination. There are 10, I need to choose any 3 of them. So 10 factorial over 3 factorial times 7 factorial. Now it's going to come out to be the same thing anyway. That would have worked. No, that'd be 720. That's only 120. So there's 120 different ways pizzas I can make. I was over here doing a permutation, which it matters which topping you pick first, but it doesn't. They're all going to end up on the pizza. If you can choose any number of toppings. Now, so the problem is we'd have to do 10C0 plus 10C1, 10C2, 10C3, 10C4, 10C5, all the way up to this. But we essentially, if you think about having, if you give each of the 10 toppings a spice, you can choose yes or no for each, which means I have 2 choices for each of the potential toppings, which is the same thing as 2 to the 10th. So total, there are 1,024 different pizzas that I can make. So do I want topping 1? Yes, no. Do I want topping 2? Yes, no. Topping 3? Yes, no. So that's down here. There are 2 to the nth subsets of a set with n objects. So all possible combinations, including the empty set, meaning you pick none of the toppings, or the entire set, you choose all the toppings. All right, so example 10, national hamburger chain used to advertise that it fixed hamburgers 256 ways because patrons could order whatever toppings they want. How many toppings must have been available? So 2 to some power, the number of toppings I have, is equal to 256. So to get the exponential, we're going to take a log of both sides. So n ln 2 is equal to ln of 256. So I'd have this. So the natural log, now you could have used the common log, 256 divided by the natural log of 2 gives you 8. So in order to have 256 different hamburgers, they only had to have 8 toppings total, because you could yes or no how many of them. Now if you think about it, 2, 4, 8, 16, 32, 64, 128, 256. 1, 2, 3, 4, 5, 6, 7, 8 possible choices you have to make. And since each one has 2, you just keep doubling. And that is just at the end of the section.